Okay. My name is Suleiman from Sheikh Abubakar Bumi Academy, a mathematics teacher. How are you doing? And how is your holiday? Okay. We just have to use this opportunity to get to you so that you will not stay idle. Okay. We are going to look at this topic, number basis. Okay. And this is SS1 topic. SS1 topic first one. Okay. Number basis. Okay, we all count in base 10 right from childhood. Okay, the way we count is in base 10, even though we might not know how we count in base 10. Okay, we count maybe because we have 10 fingers. Okay, our digit, any number you call today, make use of these 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the integers we use to form our numbers, okay? Then we count in base 10. That does not mean that it's only base 10 that we have. We also have other bases like base 2. Base 2. In base 2, remember in base 10 we have 0 to 9. 9 is the highest. In base 2, we have 0 and 1, okay? And computer makes use of binary. We human, we use base 10, computer uses binary, okay? We also have base 3. Base 3 is 0, 1, 2. Base 4, which is 0, 1, 2, 3. And so on, okay? Then, if you look at our system of counting today, due to the place value, okay, we can count up to 100, 1,000, million, billion, okay? It is possible, okay? You cannot compare our number-based system to, let's say, Roman numeral. If you look at Roman numeral, it is not, it has to be discontinued because with Roman numeral, we don't have figures to represent large numbers. As you can see, sometimes we have to assign a letter to represent number, okay, value, XL, even M. So at a point you have to get confused. Okay. Now, do you know why Roman numerals suffered? It is because they could not discover 0. Okay. This 0 you are seeing today, it is what makes our number system works. Okay. Now you can count from 0 to 1,000, 1 billion. So what makes it possible? Okay, let us look at our place value. Let's say you have a banana. Then, you have to start counting. Okay, at the point you have no banana, that is 0 banana, then you count 1 banana, 2, 3, 4, 5, 6, 7, 8, 9. And maybe you have more than 100 bananas, okay? So, but we have exhausted all the digits we have in this 10. So what do? That's a problem, okay? But with the help of place value, we have counted 9 bananas. Okay, 0 is not part. So what do? There's no symbol again because we have exhausted all the digits that is available, 0 to 9. So what do? We have to create another column, okay? So if I have to add 1 more banana to make it 10 banana, then I have to come to this place, okay, and write 1, okay? And let's say a basket. This is 1 basket. Okay, this basket contains 10 bananas. Okay, so we can now have 1, 0. Okay, that's why this place is ones, just one, and this place is tens. Whatever you have here represents 10. Okay, so let's say I need to continue. Right now I have 10 bananas. So let me continue again. So if I have to continue, okay, I now have 10 bananas. Let me continue. Let me add one. That is, it will make it 11, 12, 13, 14, 15, 16, 17, 18, 19 bananas. Okay, so at a point, I have run out of all the digits that's available. So what do? I must continue counting. So by the time I add one more banana, I have to come to this tens again and have this basket. Okay, then just write 2. So this basket represents 10, 10. That means we now have 20 bananas. Okay, at a point we may have if we continue the same pattern, at a point we have this. Let me make it 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this 1, 2, 3, 4. Remember, each pack is 9, 10. We now have 90 bananas. Okay, as it is, we now have 90 bananas because 1, 2, 3, 4, 5, 6, 7, 8, 9. So then, and we must continue counting. So let's see. This is 91, 92, 93, 94, 95, 96, 97, 98, 99. Another problem because we have exhausted all the digits. And here, we have also exhausted all the digits, which is 0 to 9. So what do? By the time I add one more banana to make it 10, of course, this one too will become, so this one will not work. So, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So by the time I add one more banana, then I need to create another column, okay, and write 100. Okay, so this is now, this basket, why this one represents 10, 10? This basket will now represent 100. That means for this basket, I have 100 bananas. So if you have 2 of this basket, you have 200 bananas. So you can see I have created another place value unit, tens and 100. So this is how we are going to continue counting. So with this system, you can count to as far as you can without confusion because of our place value. I hope this is clear. Then let us go back to our natural number, which is we call base 10. Okay, our numbers are in base 10. Okay, from this, let's say 4 to 5. The place value of 5 here is 1 from my explanation. Okay, it's just like here we have just 9 banana. Okay, whatever you have here is just 1, just like we have just 9 banana. So whatever you have here is 10. Okay, meaning we have 20 bananas. That's what we have. This is unit, this is tens. These two represent 20. Okay, whatever you have here represent 100. Okay, these 4 represent 100. We have 1, 2, 3, 4 baskets, and each basket represents 100. Okay, then I'm sure you can recall this number. This is same as 400. Okay, this is 425. Okay, in standard form, if you add, it is still 425. Okay, and in standard form, this is going to be 4 times 10 raised to the power 2, and this is 2 times 10 raised to the power 1, and this is 5 times 10 raised to the power 0. And remember, anything raised to the power 0 is 1. Okay, so with this, you see that our natural numbers are in base 10. Okay, that is base 10 for you. The place value, if you have to find the place value, let's say for 8, 9, 6. The place value of 6 here is just 1. Then how do you know the place value of the next? From one digit to another, it is a multiple of 10. Okay, 1 times 10 is 10. 10 times 10 is 100. Okay, 100 times 10 is 1,000. That is why the place value of 4 here is 4,000. The place value of 8 here is 800. The place value of 9 here is 90. The place value of 6 here is 1. Okay, that is base 10. Okay, let us quickly look at we have considered the whole number. Let us look at decimal part. When you have 4896.513, okay? Then, this is what you call point, okay? This is point. The point separates the whole number, okay, from the decimal. The point separates the whole number from the decimal. While this is increasing by 1, okay, by 10, multiple of 10. This one too is the opposite, okay, is the opposite. The value of 5 here, this same thing as 5 times 10 raised to the power minus 1, okay, 10 raised to the power minus 2, 10 raised to the power minus 3. The value of 5 here, is 5 over 10, is decimal, okay. The value of 1 here is 1 over 100, and the value of 3 here is 3 over 1000, okay. This is base 10. Let us quickly look at binary, because these are the two common bases, base 10 and binary, okay. Let us quickly look at binary. Let me clean here. Okay, let me fix this. Okay, remember a binary is always it's either 0 or 1. Binary. It's either 0 or 1, okay? 0 or 1. 0 or 1, okay? 0 means off and 1 means on, okay? Our computer uses binary. Yes, okay? But how is it possible? But sometimes you might ask, what if we dial 8? Like, how does computer recognize it? So let me tell you, it is automatically converted to binary. Okay, even our calculators, some calculators can convert this to binary. But maybe what you should ask me is this: what if we type letters? How is it converted to binary? Okay, there's what you call ASCII. Okay, A means American Standard Code. I've forgotten them. I forgot them. I'll remember later. So we have this. It's an organization. Okay, they assign value. Okay, for letters and symbols. Because if you look at our computers, there are three things you can see in our computer. You see that number, as in natural numbers. We have letters and we have symbols or sign. Okay. Of course, when you dial 0, computer will take it easy. When you dial 1, it is certain, understood, okay? But whenever you type letters like H, so with this ASCII, it's American organization that assign value for letters and symbols. Like letter H, for instance, is 104, which means anytime you type H, for instance, in your computer or any networking device, is 104. This 104 will now be converted to binary, okay? Will now be converted to binary. And remember, small letter, this character, small h, is not the same thing as H, big capital H. So which means whenever you dial this thing, I think I remember it's 074, okay? So that is how computer uses binary. So which means at the end, everything in computer is binary. Even our pictures, yes. Pictures as well. Pictures, music, okay? Remember all those things, they are just like graph, graph which is vertical and horizontal, okay? Maybe by the time you see music like this, whenever you see, so, they are represented by numbers that will make it high, the tone, and all those things. So, and each number will eventually be converted to binary, okay? So, what I want us to look at here is the place value. Let me use here. I'm going to send you a note later. Binary. This is binary. Okay, let us see the place value. Just like base 10, whatever is we have in base 10 is also obtainable in binary. Remember, base 10 is increasing by 10. The first digit is always 1. Okay, the place value, this is 1. This is 10 because it's increasing by 10. 100 and 1000. Okay, that is how base 10 works. Okay, binary, since for the fact that binary is in base 2. Okay, so the place value of 1 here is 1. Then it keeps increasing by multiples of 2. This is 1, this is 2, this is 4, this is 8, okay, and this is 16. So which means if this number 10111, okay, if you convert it to base 10, it is 1 times 16, that is 16. 0 times 8 is 0, forget it. 1 times 4 is 4, that is plus 4. 1 times 2 is 2 plus 2. 1 times 1 is 1, okay? Then 16 plus 4 is 20, 22, 23. Can you see the idea of place value? With the idea of place value, you can convert any number to base 10 easily. Okay, let me give you another binary value so that we convert it to base 10. I want us to use the place value system because I'm sure you're used to this method of conversion whereby you have 0, 1, 2, 3. I'm sure you're used to this whereby you say 1 times 2 raised to the power 3 plus 0 times 2 raised to the power 2 plus 0 times 2 raised to the power 1 plus 1 times 2 raised to the power 0. I'm sure you're used to this, okay? But I don't want it this time around, okay? So I want us to understand place value because most times if you ask us mainly to tell us the place value of 4 here, they can tell us easily without wasting time is 40. But if I ask you to tell me the place value of 0 here, in fact, you might have to, sometimes you feel like how or it's not possible. So let me rule it. Then place value of binary, here is 1. If any number base, whether base 2, base 3, here is always 1. If it is base 3, you keep multiplying by 3. 3, 9, 27 or so. So base 2, this is 1, this is 2, this is 4, and this is 8. Okay, which means the place value of 4 here is 4 times 10, 40. Okay, then the place value of 0 here is 0 times 2, 0. The place value of 0 here is 0 times 4, 0. But the place value of 1 in this, the place value of 1 here is 8. Okay, so let us quickly convert this binary to base 10. 1 times 8 is 8, 0 times 4 is 0, 0 times 2 is 0, 1 times 1 is 1, okay? 0 plus 1 is 9, this is 9 in binary. Assuming you have to okay, let us look at other base. Let's say base 3. This number is in base 3. Remember, if you are looking at base, like base 3, all the digits should be less than 3. Okay, the fastest way to convert this to base 10 is to look at the place value. Okay, we have 2, 1, 1. Okay, like this is base 3. If base 10 we multiply by 10, 10, 10. So base 3 we have to keep multiplying by 3. Sorry, this is 1 place value. 1 times 3, this is 3. Okay, 3 times 3, 9. This is 9. Okay, so the place value of 2 here is 18. Okay, so this number 211 to base 3 is 2 times 9, 18. 1 times 3, 3. 1 times 1, 1. So and then we have 18 plus 3 is 21. 21 plus 1 is 22 in base 10. Okay, so with this method, I believe you can convert from other bases to base 10 easily. Okay, but before we end this lesson, let us do the opposite. We have learned how to convert from other bases to base 10. This is base 2, we converted it to base 10. We may not write the base, okay? This is 211 in base 3, we converted it to base 10, okay? Now let's see how we convert from base 10 to other bases, okay? Base 10 to other bases. Okay, base 10 to other bases. Okay, what you do, let me just give an example. Let's say 40 to base 2 is base 10 to base 2. Very simple. We are going to keep dividing by 2 and keep our remainder. As simple as that. Okay, so assuming we have to convert to base 3, we keep dividing by 3 throughout. Okay, 2 in 40, 20 remainder. Okay, let me just do this. 2 in 40, 20 remainder 0. 2 here, 10 remainder 0. 2 here, 5 remainder 0. 2 in 5, 2 remainder 1. Okay, 2 in 2, 1 remainder nothing. Okay, 2 can no longer go in 1 because 1 is smaller. You write 0, you carry this 1 as remainder, and you have to move it up. Okay, so which means 14 in binary. 14 base 10 to binary is 1 0 1 0 0 0. Okay. This way we are going to stop for today. We are going to send you a note later, and I hope you understand and you enjoy the lesson. So we have to stop here. And then don't forget to always revise your notes, practice, and don't just spend this holiday sleeping, doing irrelevant things. You have to be serious, and remember, your academy is still waiting for you, okay? You have to be self-disciplined, do the right thing, and as government said, you have to stay inside and don't go out anyhow, okay? As you do that, pray wherever you are, God will bless you and your family. Bye.